Hi everyone, my name is Gabriel Hadimer. Today I'm presenting the wind tunnel data analysis I completed for this project. I worked through everything on my own using the wind tunnel dataset provided in the course. My main goal was to understand how lift and drag behave as the angle of attack changes, and how those trends influence overall aircraft performance. Even though this was all done online, the data reflects real aerodynamic behavior, so it gave me the chance to walk through the same process engineers use when evaluating an airfoil. For part 1, I focused on calculating lift using the first section of the dataset. The data included different angles of attack with the pressure differences across the airfoil. Those pressure differences are what determine the amount of lift being generated. Using the formulas from the course, I calculated the lift at each angle and then converted those angles into the lift coefficient CL, which also allows us to compare lift performance no matter the scale. This step took the raw numbers and turned them into something meaningful, showing how the airfoil's lift changes as the angle increases. This graph shows the CL value from part 1 plotted against the angle of attack. You can see a clear upward trend, which means the airfoil becomes more effective at producing lift as the angle increases. What's important is the curve starts to flatten out at around 15 degrees. That leveling suggests the approach to stall where the airfoil would begin separating, where the airflow would begin separating from the airfoil, and lift stops growing the way it did earlier. Seeing this trend in the graph helps confirm that my calculations were accurate and that the airfoil behaved exactly as theory predicts. Part 2 focused on drag. Here I worked with the second set of values in the dataset, which listed the drag forces at each angle of attack. Using those values, I calculated the drag coefficient CD. CD is useful because it shows how much aerodynamic resistance the airfoil produces as the angle increases. By comparing the drag behavior to the lift results from part 1, I could start to see the trade-off between generating more lift and dealing with higher drag. This part of the calculations really showed how performance changes when an airfoil is pushed to higher angles. In this final graph combines both parts of the project. It plots CL against CD and creates the drag polar. The drag polar lets you see aerodynamic efficiency very clearly. On the left side of the curve, you get more lift for relatively little drag, which is ideal. As the curve bends upwards, it shows that the drag becomes increasingly faster than the lift. That means an airfoil becomes less efficient at higher angles of attack. This graph ties together everything I calculated. It shows how lift and drag interact and helps explain why aircraft operate with specific angle of attack ranges. Finishing this final graph felt like completing the full aerodynamic picture, and it wrapped up the project in a very satisfying way. Thank you again. My name is Gabriel Hadimer, and this was my presentation.